to speak on analysis of surfaces, and I believe you're going to use the projector, aren't you?
Both, actually.
Both.
Well, it was a great delight to me to get the invitation to come to this wonderful seminar in honour of Dr. Greg. You can see I think people should have put their dates on there over here. So you can see I was here from 58 to 61. Some significance is about 61. You'll notice that the particular edition of the great book that was just referred to was published in 61, so some of us caught the tail end of arranging references and things of that nature, which of course taught us quite a lot about surface chemistry in passing. During this particular period, John Gregg had a small group who were not entirely working on adsorption, although we used adsorption techniques, but we were studying metal oxidation, and we went through a range of metals using a microbalance, which was a derivative of John's, Branson balance, to look at the growth of very thin layers on metals. And many of us measured the surface area of the material that was growing at the same time and tried to understand something about the way in which these thin oxides were nucleated on the surface. I did that with magnesium and its alloys. So I actually started my career in the 60s, and early in the 60s a plethora of analytical techniques began to appear on the market. We're all now bamboozled by these wide range of acronyms, but they did give us the opportunity eventually of actually measuring or analysing what was on these mysterious surfaces that I was oxidising in near vacuum conditions. And I suppose it was in about 64 that I first came across the scanning electron probe techniques, and since then I've made good use of them in various ways. Well, because of that context, Peter asked me if I would talk about the analysis of surfaces. And I've put here something I use with my students, a very large number of analytical techniques arranged in a Venn diagram, showing that they actually have different attributes, and you can actually put them into four main techniques: those with particular depth resolution, those with very good positional resolution on the surface, those with chemical state resolution, and those with resolution of the structure. You'll hear about some of that in the next talk probably. And of course these are overlapping, and so certain of them are good for various combinations, none for everything. Now the electron spectroscopies, which I want to start to talk about, are those in which electrons are ejected from the surface. They have very short mean free paths within the solid, and hence they carry very good surface-specific information, so they have depth resolution. And the electron spectroscopies which are excited by a probing electron beam also have good positional microscopes, good positional resolution. And those which are excited by an X-ray beam don't have very good positional resolution for obvious reasons, but they do have very good chemical state resolution. So I'm going to talk about a cluster of techniques that sort of sits here in this part of the Venn diagram. Now we've, over the years at Surrey, worked with all sorts of, a whole medley of surfaces and environments that we've mixed and matched in the course of our work. And I've picked out a set of them that I hope will here and there touch on things of interest to you, because I know they've been in the past of interest to John Gregg. Now the electron spectroscopies I shall talk about are of two kinds. One, the photoelectron spectroscopy, where you excite the electron with a photon. The photon is absorbed completely, so you have a unique energy in the outgoing single electron. So it's a one electron event with a unique energy there, and you can measure directly the binding energy of the electron in the orbital. And the spectrum from that is a very nice one, because it's got these very sharp photoelectron peaks, which we can use for very good chemical state resolution. Following the excitation of a core hole, as a process known as the Auger process occurs, in which an electron drops in and the other energy is passed to a third electron. which comes out. Frequently, this hole is itself excited by an incoming electron, so it sort of involves 4 electrons. As a result of that, you don't get unique energies for the photo line, which you don't see, but you see the energy of the transitions which have occurred. Now, that's the one that can be excited by a probing electron beam, so it has very good positional resolution. But because many of the electrons involved in it will often come from transition bands, they're as broad as the transition bands, and hence they tend to be very broad and to lack the chemical state information. Not always, but sometimes. I've mentioned Auger several times, and I thought, perhaps in deference to our French visitors, I would say that I think it was 2 years ago we had a very nice symposium in honour of Pierre Auger's 90th birthday, so it's a great generation. I think he found the Auger within 6 months of starting his PhD in about 1923, and he published his thesis in 26, so he's an exact contemporary. And, I owe a lot to him, I must say, as well as to you. Now, just to start the ball rolling, I've said that we're probed with an electron beam, and the Auger electrons, this is the pattern of excitation. The electron beam coming in excites a lot of X-rays, but it also excites the Auger electrons from the near surface, about 1 nanometer, and we can scan the electron beam, and we can, of course, measure the height or the intensity of particular peaks corresponding to given elements, and use that to plot maps. There's a better version of this. But in the instrument which we've got various instruments, but in the instrument which we use for this work, we collect both the X-ray and the Auger electron. So we simultaneously produce maps which have depth resolution over a micron, which is very good for looking for inclusions and junk and fibres and all sorts of particles in solids. And we also collect simultaneously with perfect register, because the same electron beam is exciting both, the surface information. So we can look at inclusions in steel, for example, and follow the chemistry associated with the corrosive attack centered around there. We've got spatial resolution of about 0.1 of a micrometer. Now, the first slide, if we could just press those on. Switch. Just shows that thin pad. And I wanted to put this up, sort of probe myself. I put this on just to show the difference between the X-ray image and the Auger image. These 2 top ones here, that's the X-ray looking deep about a micron, and that's the that's the Auger images, and these are taken together, and you can see that at the 1 nanometer depth resolution, the surface layer, although these were very well prepared, is actually fogging the surface. They're taken together, and here we're looking right through the surface fog. The standard technique which many of us use is then to etch the surface. Here we've removed 1 nanometer, it's an Auger image, and here we've removed 6 nanometers of surface material. But here's the actual bilby layer, the adsorbed layer on the surface, in practice obscuring the actual signal. But having removed that, you can see you get these very good Auger electron images of the surface. Just thought I'd give an illustration of the sort of data processing that goes on nowadays in these modern instrumental techniques. Here's the sort of map that we were just looking at with an inclusion in the surface. But if we actually plot the intensity for every pixel, the beam is being swept digitally across the image here, and if we collect every pixel and plot the intensity, we actually see that we get, of course, a change of intensity with position. And one has to arbitrarily put a box, a contour around there to produce the actual image. Now this is very subjective, and I have a young Chinese student who does some very nice work producing produced that image. We actually thought we should use it for a Christmas card and put a Chinese inscription on it. That's a bit like the mountains you see in China. If we can lift the projector just slightly with a slide box or something. Thank you. He put this together to show what we use to look for correlations between elements on the surface. We've now got this surface sensitivity, and we very often want to look for correlations between elements to see if there are surface compounds or to see if elements are correlated with particular sites on the surface. And what we do is, here for example illustrated by a map for oxygen and a map for sulfur on the surface, is to plot for every single pixel, we would plot the oxygen content, the oxygen signal and the sulfur signal, and that's the thing building up. Eventually we'll get a complete seems to be right on the edge of the manual here. So is that right on the edge of the adjustment? There we go. Thank you. So we'll get something like 15,000 pixels plotted here, and you'll see that there's, in this case, an anti-correlation. There's a cluster of pixels which are high in oxygen and low in sulfur, and a cluster which are high in sulfur and low in oxygen. And if we put a window around them, then we'll plot window 1, an inclusion of some oxide there, and window 2, some sulfide here. So we look for either correlation, or in which case we get a single blob, or anti-correlation between particular elements on the surface, and we can build up a knowledge of the surface phases. Is the best way of describing it. Now I want to go on and just show briefly some of the microelectrochemistry associated with the dissolution and corrosion of that inclusion. And to do that, I just need to refer to some work we did right very early in the 70s, about 75, which just showed that electrode surfaces have compositions which often reflect the electropotential. And this was a piece of copper, I think, which had been put into magnesium chloride and held at different potentials. Very briefly, and this is reversible. If you're in the anodic region, then you gather chloride onto the surface and you get a high chloride to magnesium ratio. If you're in this range here, you're roughly neutral, but if you go to high negative potentials, then you accumulate magnesium on the surface. So we can tell something about the surface electropotential by the ions which are actually absorbed on the surface from the solution. Now, having said that, I can go on to the next slide, which comes back to that same inclusion. Now we've got a map for iron and a map for sulfur, and you can see the sulfur inclusion sits nicely in there. It's about 1 micrometer across. It's manganese sulfide inclusion in some steel. This is the X-ray image, and we then expose it for 15 minutes to sodium chloride, and then a bit longer, 30 minutes, and so on. And you can see the manganese sulfide is gradually hydrolyzing and disappearing. But strangely, you can see a ring of sulfur appearing around the outside there. That was the first time we did it. I put it on because it's the same inclusion. Got a bit better at it. And here you can see now the sulfur inclusion producing a ring of adsorbed sulfur. And what's happening here is that here the sulfide inclusion is anodic. It's beginning to hydrolyze, and some of the sulfur is being captured by the cathode. Here you actually see the cathode around the outside. We've made calculations looking at the electrostatic modeling the distribution of potential, and it works out very nicely indeed. And I think this is the sort of first time that anyone was able to demonstrate the electrochemistry associated with corrosion on a scale of about 1 micrometer. Now we've taken that sort of thing on now these days to looking at metal matrix composite materials, where in fact you have deliberate additions of particles into a metal matrix to strengthen it. This happens to be a silicon carbide aluminium composite. And here now again we can see the sort of use of these scatter diagrams, where here we've plotted oxygen against aluminium, and you can see now we've got a strong correlation between oxygen and aluminium because there's aluminium oxide on the surface obviously. And if we pick up those pixels and colour them yellow, there's all the aluminium oxide. If we plot silicon against aluminium, well, they don't overlap at this stage, so they are forming an anti-correlation pair, and if we colour those green, there's the silicon, colour those yellow, there's the aluminium. And I wanted to show you that because just last week, a student of mine did a test. I haven't seen this slide before, so I hope I can insert it. But she was worried that the first corrosion she saw on these metal matrix composites wasn't associated with the silicon carbide, but was associated with small iron inclusions. They were iron oxide, and she thought they were good cathodes. So I suggested she did the magnesium chloride test to see if she could decorate the cathode with magnesium. And sure enough, here's a plot. You see that oxygen against magnesium, for example, the highest magnesium pixels, these forming this lobe out here, which you can just about see. If she picks up those, there's the inclusion being decorated with magnesium. So in this case, the inclusion in the centre is a cathode, and you can actually see the there's another one here that shows it. But in fact, chloride it reverses the situation, and there's a chloride ring around the outside of the magnesium. So it's completely reversible. Well, that's an example of surface analysis using the Auger electron. There we aren't using any chemical state information, and we often don't use that. I thought I'd put on, this is actually done by XPS, but I thought I'd actually put an example of work that some of our group do to characterise carbon fibre. Many of you know carbon fibre itself is activated by oxidation in order for the resin to wet the fibre in making up carbon fibre composite materials. And it's always it's nice to be able to assay the groups of the different groups on the surface. In doing that, we've actually developed tests in which we actually expose the fibre to gradually increasing strengths of, in this case, a silver nitrate solution, and plot the amount adsorbed. In fact, this is plotted in the form of a Langmuir isotherm against the solution composition normalized by the solubility of the silver nitrate. So this, in fact, is exactly what's in your book, where you talk about adsorption from solution and point out that it's very important to actually normalize the reagent you're using by dividing by the solubility, limiting solubility of the reagent. We've done the same here, but using magnesium to decorate it. So this is an example of a monovalent and a divalent ion being picked up by acidic groups generated on the surface of the carbon fibre. Now, the other great event which took place in the middle of my PhD, but was unrealised by me at the time, was that Kai Seekbarn, again a man of the same generation, I think, produced his first letter, which showed that in photoelectron spectroscopy you could actually see a shift in the spectrum peak according to the chemical state of the material. And this is his letter in physical letters, showing the first indication of a chemical shift. So that actually opens one to a whole host of surface chemistry where you can actually look at the chemical state of the adsorbent on the surface or of the surface layer. I illustrate the whole here, the way in which aluminium oxide can be recognized in the presence of aluminium metal, and enables us to deduce the actual thickness of aluminium oxide on the surface. And I also thought I'd point out that in addition you can see changes in the chemical state for obvious different states of oxygen or of carbon. Now the chemical state information in solids mainly comes from the different final states which can occur. And once you photoexcite a an electron out, although in principle that carries with it all the energy derived from the photon. In actual fact, it leaves behind energy associated with polarization of the surrounding lattice of different types. So there is a relaxation energy component which is left behind, and in the Auger process, which subsequently occurs, you get an extra dose of this relaxation because another electron comes out. So this carries twice the relaxation of that, and by comparing the position of the Auger peaks in the spectrum with those of the photo peaks, one can actually get a sensing of this local relaxation. This diagram here actually just illustrates some of the chemical shifts and some of the relaxations which occur for copper. But the relaxation energy can be picked up from the change in this distance here, the distance in kinetic energy between the photo peak and the Auger peak. And with that, a whole range of glorious chemistry comes out, and I thought I'd put this up because of the interest in clays, which was once very strong in this department under John Gregg's tutelage. Here we've used the Auger parameter, so-called, to actually measure the, to provide a measure of the relaxation energy and just show how it relates to the polarization of the structure, which you would determine from the refractive index using the Lorentz equation. In the inset diagram you can see the whole range going from silicon oxide through the nitrate to silicon, and if you enlarge the bit around the oxides, then you can see them all stretched out here, which is the behaving in a way which represents the polarizability of the oxygen in the different lattices. So here they are all spread out, and it's actually a change of the polarizability of the local oxygens to the silicon. So we're photoexciting the silicon. If you photoexcite the aluminium, compare it with the silicon, then you see that you get a regular change if the aluminium is actually in the silicon sublattice, substitutional. If it's an aluminate ion in octahedral coordination, then there's no change. Now that, as I said, is an example of where the silicon is sensing the polarizability of the bonds around it. But if we go to a monolayer situation, we then find that the closer the adsorbed molecule is to the surface, the better it's bound to the surface, the greater the relaxation component that it picks up from the surface. And going back to the carbon fiber story, here we see how the change in the Auger parameter, the relaxation energy, is changing. These lines represent the Auger parameters. From one which is unoxidized, down here, to one which has had a standard treatment. It's called 100%, but it's a standard treatment that's used in industry, with intermediate ones in between. And one interpretation of that is that the molecule, the atom which we put onto the surface to decorate the surface, is actually being drawn closer and closer into the surrounding atoms as you go up in degree of oxidation. Well, obviously that ability to recognize chemistry in the way, chemical state in that way, gives rise to all sorts of things you can do, and I've shown you some aqueous corrosion, and of course one would want to relate that back to so-called Courbet diagrams generated by another man of this generation, Marcel Courbet, who's also, I think, 90 this year, in which he showed how in his thesis it was useful to plot the phases on a diagram of electron potential against the pH of the medium in which it sits. And we can actually relate the surface structure right back to different regions of Courbet diagram. Or one can follow Ellingham, and if you're looking at metal oxidation, do things in which we measure the surface changes as a function of the free energy of formation. 2 or 3 minutes.
Okay.
Now, I haven't said anything about the other great technique for looking at surfaces, which I've put on here just to remind us what it is, which is secondary ion mass spectroscopy. We don't do very much in the end with these electron spectroscopies at the monolayer level. They're really sensitive to about 10 layers. But with secondary ion mass spectroscopy, we really can get down to 1 or 2 layers by using a high energy ion to excite something from the surface. In the old days, that is up to about 3 years ago, everyone complained that this was a very destructive technique and you'd hardly blinked before your surface had gone. But nowadays, with a time of flight SIMS instrument, you can get very good spectra. In fact, you can get complete maps using an ion dose which is only about 1/10,000th of a monolayer. So you do very little damage to the surface. I've sketched in here to try and highlight it. The sort of resolution or mass that these spectrometers have. Here we're actually going along in 0.2 of a mass unit, and this is mass 29 here, and obviously CHO and C2H5 are both nominally mass 29, but they're separated by the fact that there are 5 hydrogens on here and only 1 on there, so there's a few 0.008s, and you see we get baseline resolution between the 2 states. And this is the sort of instrument which we're using now to look at surfaces of fibers and polymerization. Now I'm going to be, that's the end of analysis, but it occurred to me that there's been, in the last 2 or 3 years, another big change, which is the introduction of scanning probe techniques where we actually use a mechanical probe. And it occurred to me that perhaps, well, I don't know, in the earliest state, this is a scanning tunneling microscope, and in the ones that I was familiar with working in IBM once, some in about 86, they had all the hallmarks of a Greg type structure. They were glued together with araldite and bits and bobs, and people were producing atomic resolution images. This one isn't much better, although it's a much more expensive one, which we use to actually image surfaces. And I wasn't invited to bring a poster, but I thought I would. And this poster's probably big enough to show you the sort of thing that can be done. We've all seen the atom images, and there's probably a lot of artifacts in there, but that's a graphite image with atomic resolution. And this is at 3,500, 350,000 times magnification, a half micron section of a carbon fibre. It's actually a 6 micron carbon fibre, and you can see all the structure on the surface very beautifully. Now this is the sort of thing where one day we actually might find those slit-like micropores. I don't know, we'll try and find. So I thought I'd leave that there as an exhibition. And there's another one which goes with it. In fact, that was produced by an atom force microscope, which is a variant of this, and I'll leave the actual microscope here. And that's pictures going from 10 micron resolution, 10 micron scan, down to about 1,000 angstrom scan of diamond. And obviously the other big topic in carbon these days is actually growing diamond films. And there's some